start. So let me introduce Paulo Santos, who is a PhD student at the Karl Friedrich von Weizsäcker Center here in Tübingen, but in a joint PhD with the Universidad Nova de Lisboa. And I mean, currently he is with a Fulbright grant in it's Pittsburgh.
Yes.
Yeah.
Yes.
In Pittsburgh, visiting Wilfried Sieg. So he will speak about k-provability in piano arithmetic. Pablo, please.
Okay, thank you very much for the introduction. And the work I'm going to present here today is a joint work with Professor Reinhard Kalle. And before actually presenting the main results of this talk, let me just make a very brief introduction to this topic. And let me do this by settling two important definitions. The first one is the notion of k-provability, and by k-provability we mean the notion of being provable for a fixed theory with at most k steps, a given number of steps, and we are going to use this notation for that concept. Moreover, I will consider the concept of the proof skeleton problem. That is the problem of deciding if a given formula has a proof whose skeleton is the considered one. And by skeleton, I mean the list of rules and axioms that were used in the proof. So in a sense, this problem has two inputs, a formula and a list of axioms and rules. And the goal is to decide, especially in a computational way, if there is a proof of the formula whose list of rules and axioms is the inputted one. Some known facts: k-provability is decidable for the sequent calculus of arithmetic, and here by sequent calculus of arithmetic, I'm assuming an infinite number of relation symbols to which we place no further axioms. K-provability is also known to be decidable for several formulations of piano arithmetic with a subtle change in the universal instantiation schema, namely this schema. And in that setting, the schema is replaced by other schemata, but equivalent series are obtained. It is yet an open problem whether k-provability for PA with the usual instantiation schema and not the previously mentioned ones is decidable or not. But it is known that the proof skeleton problem is undecidable for PA with the usual instantiation schema. So now let me say the main topics that we addressed. Firstly, we characterize some proof skeletons for which it is decidable whether a given formula has a proof whose skeleton is the considered one. And here we have a partial characterization, so this does not go against this second point. And secondly, we characterize some values of k for which the k-provability problem is decidable. And again, this does not solve completely the first problem, because the first problem is for all values of k, and we have a partial characterization of k, of some values of k. Our characterizations are natural in the sense that they emerge directly from the concept that we are given from first order logic. We make no strange concepts, and parameterized by unification algorithms. Our approach is also valid for several theories that extend PA. I'm not going to show here the details of those series, but in a very brief way, these series have to have the same logical part as PA, and they have to have an axiomatization using schemata. This is the intuitive idea behind this series. So to address k-provability in PA, we introduced an auxiliary theory, PA prime, that is equivalent to PA. And I will say just some words about this theory. Regarding PA, we considered these logical axioms in a Hilbert-style axiomatization. I'd like to emphasize here that these axioms are all schemata, in the sense that none of these axioms stand for a very concrete formula. For instance, focusing on the first axiom, this phi, this psi, and this mu do not stand for actual formulas. They stand for variables to which one can replace any formula. So in a sense, they are variable, they are formula variables. They are formulas that are standing for any instantiation of the formula. In the same fashion, this x does not stand for a concrete x. On the contrary, this is a formula. This is a variable that is denoting variables, and t is the term variable again. Besides this feature, all the rest is the same when one compares to concrete formulas and concrete variables and concrete terms. As I mentioned, these axioms are schemata. They vanish over all formulas, all variables, and moreover, let me just show you that some of the axioms have some syntactical conditions. For instance, these two. This t must be substitutable for x in phi. This is a decidable syntactical condition, and we are going to assume that all the conditions in the schemata are decidable. Furthermore, we are going to consider the two following rules. The first one is the modus ponens, and the second one is the generalization rule. Moving now from the logical part to the non-logical part of arithmetic, here I present you the well-known axioms of Robinson's arithmetic. And moreover, PA can be obtained from Q by adding the well-known induction axiom. And this axiom is again a schema, because this x does not stand for a concrete, this phi does not stand for a concrete formula, and both x and y do not stand for concrete variables. On the contrary, they vanish over all formulas and all variables. And similarly, we have here a syntactical condition that is decidable. As I mentioned, we developed a theory PA prime. I'm not going to show here the axioms, that is obtained by PA by changing both the instantiation and the induction schemata. Moreover, PA prime, we know that PA prime and PA are equivalent, but they are equivalent in a very strong sense, namely this one. These two statements are equivalent. Phi is provable in PA with k-steps, and phi is provable in PA prime with k-steps. This means that k-probability in PA and k-probability in PA prime are equivalent. Okay, so now let me show you the general idea of our approach. The main idea was to attach a meaning to the combinatorial nature of general proof structures. And here by general proof structures, I mean some sort of a schemata feature. This is because when one does proofs in a Hilbert-style system, in most cases, there are a lot of free parameters. For instance, if one considers the proof of phi implies phi, in this proof, there are a lot of formulas that do not need to be instantiated. There are a lot of formula variables that do not need to be instantiated. Moreover, phi implies phi is not only a theorem, but in a sense, it is also a schema, because we are not stating the phi implies phi for a very concrete phi. We are stating it for any possible substitution. So the goal was to generalize this, to start from axioms that are schemata, and to develop a theory to obtain provable schemata. We did this by accounting for the different ways to combine in a fixed number of steps. Keep in mind that our goal is k-probability, the axioms of the considered theory. And as I've mentioned, we did this at the schemata level. So let me now move to the more formal part. I will start by defining more formally what a proof skeleton is, and the definition follows by induction. The basis case is very simple. AI is a proof skeleton if AI is the number of an axiom of the theory, of the list of the axioms. And here by number, I do not mean the semantical entity of number, I simply mean a symbol. The idea is that one has, in a bijective way, for each axiom, one symbol. And the induction step is again very simple. If we are given two proof skeletons, then this array of symbols where one substitutes the given proof skeletons, and this array of symbols are also proof skeletons. And as I said, proof skeletons are syntactical entities. They are array of symbols. Of course, they have an intended meaning of representing the list of axioms and rules of proofs. So, of course, the intended meaning of this symbol is that modus ponens was applied to these two ideas of proofs, and this one, that generalization was applied to some idea of a proof. We say that the proof skeleton has k steps if it has k applications of rules, and k, of course, might be 0, and this leads to the basis case of the definition. Now, I will define what a term structure is, and here I will try to account for the fact that we are given a bit more than the context of classical first order logic, in the sense that we have term variables, variable variables, and so on. And I will try to define a general notion of term to account for this entity. The basis case is the following: every variable variable, every term variable, and the symbol for 0 are term structures. And if we are given two term structures, R and S, the successor of R plus S, R times S, and this array of symbols are term structures. And in this array of symbols, this vector X stands for a list of variable variables, and this vector T stands for an array of term structures. I'd like just to observe here that this is not only a syntactical entity, so we have a symbol for this, but just like in the context of first order logic, we are going to assume that this represents substitution. So we generalize in a very simple way the substitution operation in first order logic. So this has a two-folded meaning, a two-folded representation. First of all, it represents what it is, so it is an array of symbols. And secondly, it is an array of symbols to which one is allowed to make some operation. Now we are very close to define what a schema is. And for that, I will define what a formula structure is. Just like what I did at the term level, I will do at the formula level. And then we just need to account for the syntactical conditions that appeared in the schemata that I've showed you. The basis case is very simple. Again, every formula variable is a formula structure, and an equality between term structures is a formula variable. The induction step is the following. If we are given two formula structures, F and G, the following are also formula structures. F implies G, not F, for all VF, and here V is not a concrete variable, but it is a variable variable. And again, the substitution deal in the sense that I've previously mentioned for terms. So this is an array of symbols that we are going to consider, but we implicitly are going to consider operations in them in the sense of first order logic. We say that A is an atom if A is either a formula variable or a substitution in a formula variable, or even an equality between term structures. So in a sense, this is a generalization of the basis case from before. Now we are in the situation where I can define what a schema is. We say that an array of symbols of this form, and I will further explain this, is a schema if these I and Ji's are sets of indices, if this F is a formula structure, and these AIs are atoms. Now, let me just explain this further. So the formula structure was defined before. Here, I'm emphasizing the dependence on the formula variables, on the term variables, and on the variable variables. So far, so good. And then we have here this part. And this part is here to represent the conditions from the schemata. For instance, the one that I've showed you in the axiomatization of TA. Here, this C stands for syntactical representation of the conditions. So for each condition, we have a symbol. These conditions might depend on atoms, term variables, and variable variables. Of course, one can generalize this for formula variables in a very simple way. And now focusing on this part, these are syntactical representations of the meta-connectives. These connectives are not to be confused with the connectives here from the logical part. These are meta in the sense that they are different and they talk about these very entities, the formal structures. And we assume all the propositional logical features for propositional classical logical features for these connectives, in the sense that this one represents negation, that negation to an odd power simply gives negation, negation to an even power deletes negation, that this symbol represents a form of conjunction, this one represents a form of disjunction, that we are given the De Morgan rules, a form of disjunctive normal form, conjunctive normal form, and so on and so forth. Okay, so far so good. And again, we made several conventions that are simply a generalization from the conventions from first order logic. A substitution is a function that assigns formal variables to formal structures, term variables to term structures, and variable variables to variable variables. So in a sense, a substitution starts from a schema and instantiates it. It makes the schema more concrete, in the sense that we are substituting the formula variable to by a more concrete formula structure, the term variable by a more concrete term structure, and we are allowed to change the variable variable. Now we can define what a provable schemata is by induction. Every schema that is an axiom is a provable schema. If we are given, and now the induction step, let us assume that we are given two provable schemata, the red one and the blue one. And here, again, we have the formula structure, the conditions, and again, the formula structures and the conditions. And here, I just like to emphasize that in the red part, we have an implication. G implies H. Let us further assume that there is a substitution sigma that has this property. So let us analyze this. This means that the sigma of F is equal to sigma of G. In a sense, F can be instantiated in such a way that it coincides with the same instantiation made to G. So in a very naive way, F can be fitted into, F and G can be fitted in a common shape, in a common, more concrete shape. So again, with this naive view, if sigma of F is equal to sigma of G and F is provable and G implies H is provable, in a very intuitive way, one feels that one should also say that sigma of H is provable, and that is simply what we do. So this is a generalization of modus ponens. In the previous condition, sigma of H is provable. Of course, one needs to account for the syntactical conditions from the red part, and then we add the syntactical conditions from the blue part, and we are also allowed to add some other conditions if one desires to do so. This is a provable schemata that corresponds to a generalization of modus ponens, and the generalization of, bad choice of words, but the generalization of the generalization rule is this one, is simply starting from the blue one, placing a universal quantification, and we are allowed to add some conditions again. Okay. Now we say that the provable schema is provable in case steps if in the previous construction, as the provable schema were used at case steps. And now I am going to create a semantics for the proof skeleton in the context of provable schema. A provable schema that is an axiom has skeleton equal to the number of the axiom, the syntactical entity. And now the induction step, if a provable schema S has skeleton cursive S, then the corresponding one to the generalization rule has this schema, and similarly for modus ponens, the schema is given by this array of symbols. So far, I have addressed substitutions inside the context of schemata. Now I will make a connection to the actual logic, if one may say so. We say that sigma is a concrete substitution for this schema if it does what I've mentioned in the beginning, namely that it assigns formula variables to actual variables, term variables to actual terms, and variable variables to actual variables in such a way that this syntactical condition, now looked in the semantical eyes, is a true condition. Okay? Now, a very important theorem. This is in a sense a sounding theorem to show that our notions are sound. it states that the two following statements are equivalent. The first one is that phi is k-step provable in T. And the second one is that there are a provable schema in k steps and a concrete substitution such that the image of the schema is the formula. So this means that to see if a formula is k-step provable in a theory, this fact is equivalent to test if there is a provable schema in k steps and a substitution such that the formula phi can be fitted in the shape of the schema. So this means that we are not going outside. We are not going outside the context of first order logic, provability in that context. Moreover, this move is decidable in the sense that given a schema in the formula, it is decidable whether there is a concrete substitution such that the image of the schema for that substitution, of course, is the formula. This might seem obvious from the fitting part in the sense of the formula fitting the formula structure, but this is not so obvious in the condition part. Nevertheless, we have the result. Now I will show you the main results. And here I'm going to show the approach that we have that we chose. So we say that the proof skeleton S is stable for a fixed theory, of course, if there is a finite list of provable schemata, this one, such that it satisfies the stability condition. Namely, a formula has a proof whose skeleton is the stable one, exactly when there is a schema in the list, the finite list, and a concrete substitution such that the image of the schema is the formula. So in a sense, a proof skeleton is stable if the following two statements are equivalent. A formula as a proof skeleton is S, and seeing if the formula fits any of the elements of the list. In other words, to check if a formula has a proof skeleton is a stable one, it suffices to see if the formula fits any of the provable schemata in the list. And this can be done, of course, in a decidable way, as I've mentioned. We say that the number k is stable if all proof skeletons with length at most k are stable. And this is the general approach that we have taken, namely to construct finite lists. Now, some important results regarding stability. If a proof skeleton is stable, then the proof skeleton problem for that proof skeleton is decidable in the sense that it is decidable whether a formula as the proof skeleton is a stable one. Moreover, for the k stable numbers, the k-provability problem is decidable. And one interesting fact is that there is a maximum stable number for PA prime, and of course for PA. Okay, now I'm going to show you the idea of an algorithm that we have developed. This algorithm is not very interesting by its own. We developed this algorithm to guarantee that a general class of algorithms that we assumed is not empty. Okay, so to develop this algorithm, we consider this reference where one knows from it that second order unification is in general undecidable. And the paper, the proof is achieved by representing in the context of second order unification numerals, addition, and multiplication. And this is delivered by equations that include this one, where here S stands for unary function symbol and this circle for a binary one. And here I'm using the notation of the paper, of course. And I would like to emphasize here two aspects of this equation. The first one is that we have occurrences in both sides of the equation of the same term variable. For instance, here we have a tau, and again a tau and a tau in the second equation. Moreover, we have occurrences of variables being replaced by something where that very variable occurs. For instance, here C is being replaced by a term where that very C occurs, so the term is getting large. And this is essential. These two features are essential to the proof. We created then an algorithm that is able to solve some, and not all, systems of this form, where these R and S's are term structures. And by a solution, I simply mean a common substitution at the syntactical level, of course, to the left and to the right, such that one achieves equality between them. And again, I emphasize this is substitutions in the context of schemata. These are not concrete substitutions. The main move that we made to create this algorithm was to force the algorithm not to have the needed conditions for the previous proof, namely the occurrence of the same term variable in both sides and a variable being replaced by a term where that very variable occurs. Of course, there is a cost to this approach, namely that the algorithm might reject or even not out systems that indeed have a solution. All this to guarantee that the algorithms that I'm going to show now in this convention do exist. At least there is one, the one that we have constructed. So now I'm moving to the general approach. I'm going to assume that A is any algorithm that solves some unification problem of terms, of course, for instance, by a case analysis, and with some situations where it might output problem, and the output of problem simply means that it is not able to continue. For instance, the previous algorithm might output problem when it identifies the conditions of the proof. We assume that A also gives some important information. This is useful for the proofs for the theorems ahead. And more importantly, we assume the following feature that we call the subproperty. If A is a successful system, if A is a successful algorithm for this system, and by successful, I simply mean that it helps and does not output problem, and there are concrete substitutions to the left and to the right, such that one achieves equality, then one can guarantee a solution given by the algorithm and a concrete substitution, such that this occurs. So the left part was given, also the right part, and the idea is that one can factor inside the concrete substitution this general substitution sigma, this one, the one given by the algorithm. Okay, that is not a very strong property, by the way. So we then took the list approach, in the sense, the approach by where we construct lists. So for each algorithm, we created finite lists for each value of k of provable schemata and proof skeletons and of course these lists within this k of provable schemata consists of provable schemata in k steps, and the same feature for proof skeletons with k steps. We say, this is a concept similar to the one from before, from stability. We say that the proof skeleton S is grounded for the algorithm A, and this notion does depend on the algorithm if A is in this list, if S is in this list, where this K is in this K is simply the number of steps of the proof skeleton. Moreover, we say that K is a grounded number for the algorithm if all proof skeletons whose number of steps is at most K are grounded for the algorithm. We are going to consider the union of the lists simply by omitting the K. Now the main results. The first one is that for grounded proof skeletons for a fixed algorithm, the proof skeleton problem is decidable for these grounded ones. So it is decidable whether there is a proof of the formula phi whose skeleton is the considered one. And again, this depends on the algorithm. Different algorithms might give rise to different grounded proof skeletons. Moreover, we have this fact: for k, a grounded number for the given algorithm, to see if a formula is k-step provable in T, it suffices to see if there is a schema in the list constructed by the algorithm and a concrete substitution such that the image of the schema is a substitution. This theorem is important to obtain the next one, namely that for grounded numbers for a fixed algorithm, for grounded case, the k-provability problem is decidable. Of course, this applies in particular for PA prime, the theory that I've introduced in the beginning, namely for each grounded number, for each k a grounded number, k-provability in PA prime is decidable. Using the fact that k-provability in PA and PA prime are equivalent, one obtains this consequence, namely that given k a grounded number, for A in PA prime, k-provability now for PA and not PA prime is decidable. And these numbers are being obtained not from PA, but from PA prime. One could wonder if this approach is in fact limited or not, in the sense that it could be the case that in fact one was only constructing for a given algorithm a finite number of proof skeletons, but that is not the case, and this is delivered by this theorem. For every algorithm A, there is an infinity of schemata in this union. So this means that the lists, when one goes through the hierarchy of lists, when one increases the number of steps, one is obtaining more information. The information is not limited. Finally, my last result is this one, and it says that one can abstract the algorithm and develop a general algorithm to which one inputs algorithms to solve the previous problem. More precisely, given an algorithm A, there is a general algorithm depending on this algorithm A that has the following property. For each grounded proof skeleton and formula phi, the algorithm halts and accepts S and phi exactly when phi as a proof skeleton is S. This means that there is a general algorithm to which one inputs a fixed algorithm A, and this algorithm solves the ground proof skeletons for A, the grounded proof skeleton problem for A. To conclude, I've shown you some important concepts on k-provability and on proof skeletons. I've showed you, I've generalized the concept of a schema to a more syntactical approach. I've generalized the concept of provable formula to the concept of provable schema. And then, using these technical features, I've shown you how we address this issue, namely by creating lists, finite lists that depend on algorithms to solve partially these problems. That's it. Thank you for your attention.